So this is where I was at the last time. If I have X, an affine algebraic variety, it has a coordinate ring, K of X, so it has this thing called a coordinate ring, and so this is basically polynomial functions so I don't want to go through this again. If X is given embedded, then it's just the coordinates, the polynomial functions on the ambient space restricted to X. The definition of algebraic variety means that this does not depend on which particular embedding I've chosen. Right? So I'm going to assume usually assume that X is irreducible. So for most of what I'm saying, X is irreducible. So we need it for this definition. So X is irreducible, of course, is just the same thing as saying the ideal defining X in some embedding is a prime ideal, and that's the same thing as saying that K of X is an integral domain. So then, so the definition of rational function. So first of all, we define the rational function field K of X. This is the ring of fractions, the field of fractions of K of X. Right. So I've got an integral domain K of X. So it can be put inside a field K of X. And the field consists of, this is the set of all formal expressions f over g. So I want f and g in the ring. And g not equal to 0. And then divided out by the equivalence relation, f over g equals f primed over g primed, if and only if f g primed equals f prime g. So this notation f over g is a notation for the equivalence class. So when you do this with integers, you say, well, if f and g have a common factor, I can cancel it. However, you have to be a little bit careful because NB, this equivalence, the equivalence relation, this star is a bit stronger than just cancelling common factors. When K of X is not a UFD. Okay, so I mean, example, if I take K of X1 up to Xn, then this is a UFD. And if I do the field of fractions, K of X1 up to Xn, so I do K of field of fractions, rational functions in K of X1 up to Xn. So this is, I can write everything P over Q, where these are polynomials and no common factor, no common factors. And then up to scalar multiples, the P and Q are essentially unique. P and Q unique up to scalars in K. So non-zero. Okay? But if this depends on this, saying that I can make P and Q polynomials with no common factors depends on the ring being a UFD. So e.g., if another example. So if I take, for example, the ring of XYZT divided out by xt equals yz. Yes? Then you can prove that x and y, z, t are irreducible right? So I've got a certain ring here, and the guys x, y, z, and t are irreducible but not prime. So this is, in a certain sense, this is the most obvious, the most basic ring which is not a unique factorization domain. So I have x times t equals y times z, but x does not divide y or z. Right, so I managed to get a. So this is one of the examples. So this is one of the problems I set on the example sheet to do this properly, right? And this means that if I take, for example, y over x, well, it's the same thing as t over z. Right, and so here I'm getting two different relations, but basically y and x and t and z have got nothing to do with each other. The as elements in the function field, they're the same elements, but the numerator and the denominator are quite different. So this is just to warn you that this equivalence relation star has some slightly non-trivial slightly unexpected properties if the ring that you're working with is not a UFD. Okay? So, so why do we bother? So why bother? Well, there are really several reasons. So one is we want an open set U in X, Zariski open set. We want to have a structure of algebraic variety. Right, so, but it's certainly not affine. It's usually not affine. So, for example, if I do A2 and then I delete the origin, so this is, you can think of this, for example, as being A2 with x equals 0, and then union A2 less y equals 0. And either of these, we'll see later, either of these is an affine variety. Right. Basically, I can. These are like if I write down the graph of the hyperbola, if I write down the graph of 1 over x, then we're going to see that this is just isomorphic to this variety. Right. So I'm doing something that's sort of basically pretty natural here. I'm taking A2 and I'm just saying, well, I'm going to consider this little affine. I'm going to take this little open set. So you know, I want it to be an algebraic variety. It's a perfectly easy thing, but it's not. Whatever else it is, it's not an affine variety. You can prove this in the again on the example sheet. And so what is it? Well, you know, here I have k of x, y, and x to the minus 1. And here I have k of x, y, and y to the minus 1. And between them, so each of these defines the structure of an algebraic variety on the two open pieces, but they involve these rational functions. So I can think of this as being obtained by gluing together two pieces. Right? So this is one reason. And the second reason is that, so this is because I want to go from x to u, but if I have x affine, I might want to put this in a projective space, Pn, and take projective closure in there. So this is a projective. And then how do you define the structure of an algebraic variety on a projective variety? On a projective algebraic set, just think of, I'm writing down, for example, a single equation, a single homogeneous equation in Pn. So it turns out that the right way to do this is use rational functions. So I repeat, I'm working here with an affine algebraic variety. Then I've already got this sort of quite, big, helpful, useful set of polynomial functions on it. So I can use that to do various things, including embedding it in space using just x1 up to xn, or re-embedding it in some different space using different polynomials, making maps between x to y and so on, all in terms of these polynomial functions. So here, I've already got a big set of functions, and maybe I don't need to do this, right? But on projective space, well, we're going to see when we introduce projective space, basically, there are just no globally defined polynomial functions. So there are no, I'll come to this. So there are no globally defined polynomial functions on x bar, except the constants. Right, and so there's something going wrong here, and on Pn, what I want to do is put inside here an, which is where xi is not equal to 0, and then I have x1 over xi, so x0 over xi, x2 over xi. Right, and I get affine coordinates. But if you think about these affine coordinates, they're really rational functions. They're really denominators. If I try to compare what happens on one affine piece or on a different affine piece, I get basically this situation. I get something quite similar to this. Anyway, sometimes understanding why you're doing something is harder than just doing it. So let's, for the moment, not worry too much about why I'm doing it and just say, I'm going to study these so obviously the first thing to say is a rational function. So a rational function, this is just a definition. So this is, let's sort of say f is an element of this k of x. So this means that f can be written as g over h. Right? And so, you know, the thing that's written on the right here is an expression in k of x. Right, so it's a representative of this equivalence relation. So I'm taking this f over g, this element f over g. And so what do, you know, and I warned you that it can happen, it might happen, and it does happen in practice, that there are several, you know, possibly quite different expressions for one and the same f. So this f is not defined not necessarily, usually not defined everywhere. So the given expression, g over h, is not defined where this h is 0. But maybe there's some other expression where it is defined. So the important thing is to find out, is to sort of make this clear. So, you know, rational function means a function that's not a function. I mean, there's a kind of contradiction in language here because, you know, function is a noun and rational is an adjective. An adjective should modify the noun rather than destroy its meaning. So rational means not everywhere defined. A function, as you all know, in set theory is everywhere defined. So this is something which is everywhere defined, which is not everywhere defined. So this is sort of cheating. It's incorrect language. But anyway, we're going to sort of come to that by saying that f is regular at p in x if there exists an expression. If there exists an expression f equals g over h with h of p not 0. Right. So you know, I just repeat just one more time. This g over h is a particular expression for a fraction. So it's I've chosen numerator and denominator here. I'm writing g over h. Right? And it's possible that there's some other completely different expression, g over h, which represents the same function. Right? So here I'm saying there exists an expression, so one of the several expressions for this. So you know, what am I thinking about? I'm thinking, well, you know, here is my variety. Here's my variety x, and then I write down f is g over h, and then maybe here is h equals 0. Right, and so I should, at least the expression g over h doesn't make sense there. Right, so we're expecting that f isn't regular. It's not regular. Possibly where h is not 0. Okay, and what do you see about this h? Well, it's an algebraic subvariety. So h equals 0 is an algebraic subvariety of x. And the complement, h not equal to 0, is a Zariski open set. right? And you know, it's always part of the definition here. When you say field, you're not allowed to divide by 0. So the guys that appear in the denominator here, they're not allowed to be 0 as elements of the ring. And so this H not equal to 0 is a Zariski open set, and it's not the whole of X. Right? And my X was irreducible. So, so this set is a Zariski, a dense open set. In the Zariski topology. Okay, so there are, you know, there are the suspicious points, the points where at least some expression of f, some expression of f as a fraction of polynomial functions doesn't work, and that these, for any such expression, this locus is just, you know, is a closed subset, which is not the whole of X. So, so this is one definition. I'm saying, suppose I fix P, then I can ask this question: is F regular at P? And so let's ask now. Let's fix F and ask for what P is it regular. So now, given F, we write the domain of F. This is domain, or domain of regularity, of definition, or of regularity. So this is the set of points P such that F is regular at P. Right. So the thing I want to say is what I said here about this particular expression, this h not equal to 0. So this is just a definition. Okay, now what I want to say is that domain of F inside X is a Zariski dense open set. So this is a proposition. Let me state it all. It's useful to sort of have it all together. So I gave a little argument for that. The argument's not correct yet, but it sort of gives the idea. So second, if domain of F is the whole of X, then actually, then F is in K of X. Right? Then my F was not a rational function at all. It was just an ordinary polynomial. Right? And there's a third statement here which is also convenient to say. So if G is in K of X and if G is in K of X and F is regular at P for all P such that G of P is not 0, then F is in K of X 1 over G. Okay, so this is in K of X, right? And so an element here. This is the ring generated by polynomial ring, by coordinate ring K of x, and this one element 1 over g. So this 1 over g, I can do polynomial combinations of it. In particular, I can do 1 over g to the power of n. So the statement here is that if f is regular at p, whenever g is not 0, then this means g to some large power times f is actually regular. Okay, so let me just say why all this is true. So it's basically just thinking about, I should say, so here K is algebraically closed. Right. So I'm in the framework of the Null-Stern-Satz. I'm going to use the Null-Stern-Satz in the proof here. Okay, so one domain of f is. So what do I want to say? It's a set of points. So let's say what V minus the domain of f is. X minus the domain of f. So what does this mean? It means P is in X, and for all expressions, every time I make an expression f is g over h, then h of p is 0. Right? And so this set here, this is equal to the variety of, so what do I want to say? I want to say df, where df is the ideal of denominators of f. So we can say this is the same thing as the set of g in k of x, set of h in k of x, such that h times g is in k of x. Right, maybe union 0. Okay, so shall I say this again? So whenever I've got an expression f is g over h, then the set of points where h is not 0 is part of the domain of f. So those are the good points. Those are the points where the function f is well defined. Right? So if x is not like that, it means that every time I write an expression f is g over h, then this h vanishes at the point p. Right? So then it means there's no way that that any expression like this can be regular at p. Right? So I say that's the same thing as every denominator, every possible denominator of f vanishes at the point. So this is the variety defined by, this is a set of points where all of these guys vanish. Right? So if I write it like this, the ideal of denominators of f, then this is a set of denominators of f together with 0, then it's clear this is an ideal. Right? Because if I have the product, if I have the sum of, think about h1 plus h2 multiplied by f, that'll be in there, and think about a times h times f, that'll still be there. Right? So this is clearly an ideal. Obvious that this is an ideal. Right. And so this guy here is a Zariski closed set. It's a closed set because it's a variety defined by a certain ideal. So V of D of F is Zariski closed. So therefore, domain of F is Zariski open, and it's non-empty because there's at least one expression, F is G over H, with H not equal to 0. So H is not identically 0 on K on X. H is not identically 0 on X, and this means at some points it's not 0. Okay? So that's this proves part 1. Okay? So let me say I'm going to prove 3. Now prove 3. So, and say 2 is a particular case. With G equals 1. Right. So let's not worry about 2. 2 will follow obviously if I prove 3. So the statement here is that F is regular at every point P where G is not 0. So suppose F is regular at all P where G of P is not 0. So let me write. Let me just say this again. This means that G is 0. G of P is 0 for all P in this variety of denominators of F. Right. This is just the statement, same statement. So F is regular at all points P where G of P is not 0. So if I take a point, if I take a point where F is not, if I take a place where F is not regular, then G has to be 0 there. So this is saying, I'm just saying the contrapositive of this, the logically equivalent to this is that if F is not regular at some point, then G of P is 0. Right? So wherever, so this guy here is a set of points where F is not regular, where F can't possibly be made regular. So if I have a point P in there, then G has to be 0 on it. Okay? And now this is exactly the place the statement of the no stones at. I've got some ideal here. I've got an ideal, so some funny ideal. It doesn't worry, you don't have to worry where it comes from. There's some ideal there. So I take V of I take V of that ideal, and then I have a function which vanishes on V of the ideal. So G is 0 on V of the ideal D of F. Right? And now you just have to read the statement of the no-Stones-Satz. No-Stones-Satz says that then G is in the radical of this ideal. So this is sort of very neat and very simple. If you hadn't had this idea to write the ideal of denominators, you'd have been in some embarrassment. Yeah, so so the null-Stern-Satz implies that g to the n is in denominator of f for some n. And this means that f is in kx of 1 over g. Okay, so actually it's a very simple statement as long as you have in mind that you're going to use this ideal of denominators of f. And you realize that this involves the null-Stern-Satz. Okay, so this proves the statement I proved is 3. Suppose that f is regular at every point p where g of p is not 0, then f can be written as a rational function where the only denominator is a power of g. Right, and so if g equals 1, we get statement 2. Right, this is a statement that if g is regular at every point, then f is actually a polynomial. So this is at the moment just a definition, but we're going to come back to it later in some detail. So if P is in X, define the local ring OXP. So this is the set of F in K of X. So this is still an irreducible variety. Irreducible affine variety. So this is a set of f in X, in f rational functions on X, such that f is regular at P. Okay, so this is a big idea. This is an idea that's going to go a long way. So I'm not going to say a lot about it now in today's lectures, but this will be a major topic in subsequent algebraic geometry, and in particular in the rest of the course. So let me just say in commutative algebra. In commutative algebra, a local ring A is a ring, I think I want it to be not 0. So I want, in other words, i.e. 1 is not equal to 0, such that A has a unique maximal ideal. Right. So let's just we just think about this in general. If I take A and I take element X in A, so if X is not invertible, it means that X is a non-trivial ideal. and therefore x is contained in a maximal ideal. Right? So I'm doing just commutative algebra at the moment. At the moment, I don't even assume that A, for this purposes, A doesn't even have to be an integral domain. Quite soon I'll just say, let's assume that A is an integral domain. Right? But I have a certain ring, and I have a certain element of the ring which is not invertible. Right? Not a unit. To say it's not a unit means that the set of all its multiples is not the whole of A. In particular, the element 1 in A is not there. Right? And then I just put x into a bigger ideal. I just put this into a bigger ideal, and then a bigger ideal, and then a bigger ideal. Eventually I get into a maximal ideal. So so every element which is not invertible is contained in a maximal ideal. So A is local is if and only if all the non-invertible elements of A form an ideal. M. So I have A is A multiplicative, so the units union M, and this is an ideal. So why is this guy a local ring? So in my case, OX of P. So this is the set of all F in K of X. And so I'm going to say that F can be written as G over H, so there exists an expression with H of P not 0. Right, so what does it mean to say that this element is not invertible? Can anybody see that? So I've got this F written as numerator over denominator, or possibly in the Far East you should say 1 over numerator times denominator or something, I don't know. So I've got this G over H, and so what's the inverse of G over H? If an inverse is going to exist, then you'd expect it to be of this form, H over G. Right? So when will this H over G be in there? So this is any element, and this is its possible inverse. So when is this guy in there? So this is in OX of P. If in OXP, if and only if, well, I mean, if it's in there, if G of P is not 0. Yes? So in other words, so I take so look, here's my algebraic variety. You know, maybe it's got some interesting points on it. Maybe it's got some little singular points, or maybe not. Right, let's take a point there. Right, so I've got this thing which is f, a rational function. And it's defined in the neighbourhood of this point. It's defined somewhere here. Then if it's not 0 at the point, it's a regular function in some neighbourhood of the point. If it's regular in some neighbourhood of the point and not 0, then also 1 over f is. So if f is regular at P and f of p is not 0, then also 1 over f is regular. Right. So all the guys that belong to Ox of p can be written like this: f is g over h and h is not 0. And I can take that f and I can evaluate it at p. So it makes sense. I mean, that's what being in the domain means. So take f of p. Right? F of p is now some number. If that number is not 0, then also h over g makes sense. Yes? So OXP is a ring, and the elements in it that are not invertible are the f is g over p, g over h, with h of p not 0 and g of p equals 0. Right? Or in other words, I can take OXP here and I can take a map to k sending f into f of p. So this makes sense. This expression makes sense because I can, I just said, f is g over h and the denominator is not 0. So I can evaluate g over p and h over p. That fraction is a number in k. Right? And MP is the set of f in OX of p such that f of p is 0. Right? And this is the kernel of evaluation at p. Right? And so it's an ideal. Okay, so I told you here in this spiel, in this little thing, I was telling you that a local ring is a ring where all the non-invertible elements form an ideal. Yes. So here I'm telling you that the local ring at P has the property that, well, there's a homomorphism to K, taking a function f into f evaluated at P, and the guys that are not invertible are exactly the kernel of this. Right? So, so let me say this another way. I have k of x, right? This is the coordinate ring. This is no rational functions here. This is just the ordinary coordinate ring. And inside there, let me write capital MP. So this is the maximal ideal of P in k of x. Right, and so this OXP is the set of G over H, such that H is not in MP. Right, so anything in this ring consists of rational functions with the h not vanishing at the point. right? So an expression, this expression g over h is still up to this equivalence relation, so that a guy in there may have many, many different expressions here, but he'll have at least one expression where h is not 0 at p. Right? So this is a sort of big complicated ring with lots and lots of different ideals in it. But what the effect of doing this is, if I have some ideal which is not contained in there, then when I do this, it will just go to the unit ideal. So you know, this is perhaps, for most of you, this is perhaps a new idea. So let me say again something I said 2 or 3 lectures ago. So this is just another example of a local ring. So if I take Z, this is the UFD, as you all know, and let's take P of prime. P of prime. So you know, my favourite is P equals 5, but it doesn't really matter, right? And then I can take Z in Q, right, and I can take this Z localized at 5. So this is the set of all rational numbers. This is a set of all expressions n over m, where P does not divide m. Right? So this is a local ring. This is the integers. It's the integers localized at P. So what does localized at P mean? Well, you know, in this kind of a lot of commutative algebra is really about factorization. So, as you know, if I've got a number, I can factorize it into primes. Suppose we're interested in that factorization of primes, but we're only interested in the particular prime P. For example, we might be asking how many powers of 5 divide my number. Then if we divide by some other prime, or we multiply by some other prime, it just doesn't make any difference. Right? And so this is integers considered multiplicatively, but only considered up to what power of P they contain. So this idea is important even in you know, simple elementary number theory. So this is a local ring, and the maximal ideal is P times ZP. Right? Because if I've got an expression n over m like this, where P doesn't divide m, if also P does not divide n, then I can just invert him. Right? So every element here is either in this maximal ideal, so it's a multiple of P, or it's invertible. And that's the condition for a local ring. Okay. So in the later parts of the course, I'm going to talk about algebraic curves and divisors on algebraic curves. And for algebraic curves, I'm not going to write anything down here, but I'll come back to it later. So if X is a non-singular algebraic curve, then the local rings here are discrete valuation rings. So this is also an example of a discrete valuation ring. So you know, Z, you're used to working with the ring of integers from school days, right? And you know that you can do its unique factorization domain. There's lots of tricks you can do with numbers which involve factorizing them, right? So this one here, well, there's still factorization there. It's still a unique factorization domain, but the special property it has is it only has one prime. So every element in there is some power of that prime times a unit. So this is also an example of DVR, discrete valuation ring, so namely every element of Z mod P, Z localized at P, is a power of P, P to the power of A times a unit for some P, some power A. Right. And so OVP, let me say XP for X, a non-singular algebraic curve, has the same property. Right, so I haven't said what these words mean, but later in the course I'm going to be coming back to this, and I'm going to be talking about this in some detail. So another example is I haven't sort of prepared a notation for this. Let me just write A, and so this is convergent. It's a power series in complex variable Z with non-zero radius of convergence. Right. So here I'm taking, here's the complex plane. Right, and here's the origin in the complex plane. So I want to take if I have one of these things, it's sigma ai z to the I equals 0 to infinity, right? And I'm assuming here it has some radius of convergence. So this means that the ai are bounded by, you know, some constant to the power of I. The ai don't grow too fast. Right, then this defines a holomorphic function. And if a naught is not equal to 0, then it's a holomorphic function. F, then f to the minus 1 is also holomorphic. Right, so this is this A is a local ring, and the maximal ideal is the set of F such that F at 0 is 0, and that's the ideal generated by Z. Right, because f of 0 is just picking out this first term, A0. So the power series here either has A0 equals 0, in which case it's a multiple of Z, or it's invertible. So this is a holomorphic function. If I have a holomorphic function and it's not 0, then locally near the origin it's still, the inverse is still. So these are, you know, these are motivating examples. So this is also a DVR. These are motivating examples. These are examples that you might very well, I mean, you've certainly seen this implicitly in undergraduate complex analysis. You've probably seen this in at least the idea of this in number theory. Right? These are going to be very useful for us to understand algebraic local rings of algebraic varieties. Okay, so is the definition still here? No. So in my case, X is an affine algebraic variety. I've got this ring K of X, so it's coordinate ring. I'm assuming this is irreducible, so this is a domain, an integral domain. Right, and so we defined K of X to be frac of K of X. Right, so an element in there is F is G over H, and you know, we worry about G of H being only an equivalence relation, but for any given point we can always make a choice. Right, so here I insist that H is not equal to 0 and equivalence class. Right, and then inside here I have, so if I have F in there and P in X, I have this relation saying that F is regular at P. Means there exists F equals G over H with H of P not 0. Right, this defines OX of P, so this is the set of F. F is regular at P. Yes? So if U in X is a subset, but in particular I'm thinking of a Zariski open subset, then you can define, I think, gamma of U. Let me write gamma U of X. I'm not going to use this notation anymore, but it's suggestive, and some of you will be studying other things where this notation is relevant. So this is the set of F in Kx such that F is regular at all P in U. So this is obviously a ring, and you know, when as U changes, as U goes, for example, U might get smaller and smaller, then this ring will also change, and maybe it'll get bigger and bigger. So this is the structure sheaf of an algebraic variety. I'm not going to say sheaf, at least to any extent, in the rest of the course, but you know, if you want to go from the kind of varieties that I'm talking about here to the general notion of a scheme, then you'll quite soon need notation like this. Okay, so let me. I think I'll leave it at this until the second half. So I have a new example sheet, oops, and I have the returned homework.